We have a really interesting session today with 3 students who've been doing research as part of the BU Collaboratory on different aspects of privacy and adversarial attacks. And I think you're going to find this pretty interesting. We had a 4th student who was also going to present, but unfortunately she's under the weather today. So we'll hear from her at a future RIG meeting. For those who don't usually go to RIG meetings, they're first Tuesday of the month, generally speaking. So the next one will be in March. And the notes and the agenda are at the Etherpad link that I put into the chat if you're interested in looking at past ones or past topics. Feel free to get in touch with me if you have any questions about past meetings or if you have ideas for future ones. I'm going to start recording, I hope.
Well, I already recorded, Heidi.
Oh, okay, super. Even better. That's right. I'm not running this meeting anymore. Jen Stacy has joined us.
The woman behind the curtain.
The woman behind the curtain, exactly. So she's the newest member of the organizational team that makes this possible. And she's also an important part of the Collaboratory going forward. So without further ado, let me introduce our first speaker, Cam Garrison, and his topic is, Are Adversarial Attacks a Viable Solution to Individual Data Privacy?
Awesome. Thank you so much. I'm going to share my window. Is that up for everyone?
Yes.
Yes.
Okay, awesome. Okay, nice to meet you. My name is Cameron. I'm going to be presenting on research that I did in the fall, advised by Professor Lance Galletti, and it's about privacy and adversarial attacks. So I'll get into it. Using the internet as a privacy-minded individual is very difficult. Nearly every online platform involves trusting that platform with your own personal data. Many claim to use techniques like differential privacy to hide users' information. However, as Christina's presentation later will note, many do not seem to be using these techniques to their full potential of protecting users' data. So, as a user, what can you do to protect your information while still being able to make use of these online platforms? The goal of my research last semester was to investigate techniques from the user side, which would enable them to strip sensitive information before they upload it. The primary method I investigated was the process of generating adversarial examples through adversarial attacks, which I will explain now. So what is an adversarial example? It was first defined in the groundbreaking paper, Intriguing Properties of Neural Networks, which if you're interested in neural networks, I would really recommend checking out. And in it, they found that applying an imperceptible non-random perturbation to a test image can cause it to change the network's prediction. Those modified images are known as adversarial examples. And here's a quick example on this slide. If you see on the left column, those are the ground truth images, which were all correctly classified by the model. Then in the middle is that imperceptible noise. And then on the right side, you can see the modified images, which were then all classified as ostriches by the model. So how do you then perform an adversarial attack? Anki will later give a high-level overview of adversarial attacks, but here's just one quick example of how it could work. This is known as SIMBA, simple black box attack, and it's pretty simple to use and understand. You start with your input X, find out what the model's predicted probability of the ground truth class is, then you add a delta change to the X, making X prime, and then find out what the model's predicted probability on X prime is. If the probability of the ground truth class is then lower, keep the change, otherwise you invert it, and then you iterate until it changes the prediction. This is a simple iterative attack, and it's a white box attack. You have access to the model's predictions, the model structure, and its parameters. But if you don't know anything about your model, you're performing a black box attack. The attacker has no knowledge of the model it's attacking. And this is the first type of attack I attempted in my experiments. Through experimenting, I tried a variety of techniques to fool a neural network classifier, including adding Gaussian noise in every pixel of the image on the left, adding noise that was targeted in the center of the image, and then adding noise in randomly selected pixels around an image. So these were generally unsuccessful despite my best attempts to make these naive methods work, as we'll see in these quick benchmarks from the next slide. So I created a benchmark of how often using the truly random perturbations, just distributed randomly around the image, was successful. So in use to compare against future experiments. Note that percent of successes here means percent of times that the perturbation caused the network to misclassify the image. And after this, I decided to go in a different direction with my research. In one of my classes, I learned about the game theory concept of Shapley values, which is a metric to quantify how much each feature value in a vector contributed to a model's predicted value. I realized that this technique would help us gain understanding about what pixel locations a neural network classifier deems to be important for classifying an image. And later, I realized that these values could have potential to be used to generate perturbations in images and could be part of a new adversarial attack. So before I get into how this attack works, I'll explain why I think there's value in using Shapley values in a method to generate adversarial examples. If Shapley values can be found to be relatively consistent between different neural network structures, this method could be used to attack neural network classifiers which you do not know the structure of, becoming a sort of gray box attack where you can attack a model without knowing its full structure and parameters as well as outputs. So my idea for generating adversarial examples was basically as follows. First, you generate Shapley values given a dataset and a classifier model. Then you create aggregated heat maps of these Shapley values per each class. Finally, we'll create perturbations in images at the pixel locations where the heat maps have the highest values. Next, I'll explain the dataset used and we'll get into some results. So I used the fashion MNIST dataset, which is similar to the famous MNIST dataset, except for rather than having 10 handwritten characters, it instead consists of 10 different classes of clothing images. So that's pants, shirts, shoes, bags, etc. And I used a convolutional neural network with 2 convolutional layers, and you can see its accuracies to each class on the left side of this slide. Now we'll take a look at all of the heat maps generated. So looking at these Shapley heat maps, the lighter locations in an image means a higher aggregate Shapley value and a darker means lower. And remember that a higher Shapley value means that the pixel location contributed higher on average towards the model predicting that class. The heat map to look closest at is the trousers heat map in the bottom left. That's the class that I ended up running the experiment on, where I was perturbing images of pants using heat maps from each of these 10 classes. So to interpret the image a little bit more in the trouser heat map on the bottom left, that line of light pixel locations have the highest Shapley values, meaning that they were found to be contribute highly to what the model ended up predicting. So in my mind, that's like in between the 2 legs of the pants, and that is important to what the model's predicting. So let's look at some results for this initial experiment now. Here we can find that there were actually better results than our previous random benchmark. In that right-hand column, rather than just percentage, it's actually by the best class. So in each experiment, you're perturbing values in the Shapley heat map from each class. So this is how the best class for an experiment performed. So in that first row, you can see we're perturbing at 5 pixel locations. We're adding that value of 4 at each of those locations, and the best success we got was 55%. So this is, although it's just an initial experiment and kind of a first stab at using this sort of method for adversariality, these results are still promising, and I'll show you a few images of adversarial examples generated through this method. So in the title of each of these images, you can see which class of Shapley heat maps was used to generate the perturbated locations, and note that those pixel locations are pretty obvious in this case to the eye, which is primarily because this is just a 28 by 28 pixel image. So any changes in the pixels is pretty clear. And obviously in the end goal for this method, it would be great to generate imperceptible changes, which is one of our next steps for the research, which I'll get into right now. So as I noted in the why section, it's really important for us to eventually learn how the Shapley values differ between different neural network structures on the same or similar data sets. So that's a really big next step of the sort of thing you'd like to learn about this. And then also it's just testing this method for generating adversarial examples a lot more, meaning on different data sets, different model structures, way more data, and adjusting hyperparameters like number of pixels modified and the amount that you modify that pixel location by. And then with the end goal of seeing if this method can work in a way that generates truly imperceptible changes. Something I want to emphasize is that this is all of my experiments and the models created are found in a open source repository created last year. So really it would be very useful if any more experiments could be contributed, models, really anything, or if you just like to check out the code, it's all there. So thank you all for listening. And if I'm not wrong, I think that there's time for questions.
Yes, definitely. Ari has a question.
Hi, thank you. Thank you for the presentation. How did you do your testing? Did you parallelize it?
I was doing things on the cloud, so I was using Paperspace, so it ran pretty fast. I didn't really need to parallelize my experiments. Yeah.
Well, if you want to be doing your separate, figuring out how the perturbations affect, that's all very parallelizable, right?
Great. I don't think I fully understand. I'm not like an expert in parallelization. Could you explain a little
I'm
bit?
saying that you're doing perturbations. You're perturbing. You're trying to see which perturbations affect the model result.
Yeah.
So, perturbing different parts of the image, right? These are all completely decouplable.
Yeah.
Right. So you could just throw this at a whole bunch of machines and have each one try a different perturbation.
No, I understand. That definitely seems like it would speed things up.
Yeah.
Thank you.
Thank you.
Cameron, can I ask, the slide that you had that talked about the much higher success rates, I guess I'll call it, for whether or not an image was perturbed. Yeah, thanks. So did you see any relationship here between like how many of those pixels you were inserting once you had decided you were going to concentrate on the Shapley areas? Did it matter that you did 5 versus 10 versus 20? That looked like what you were doing before.
Yeah, absolutely. Yeah, but the difference in the average values of like class percentage between 5 and 20 was really huge. Like in the case where in that bottom row, see how like the best class percentage was 100. Most classes were close to 100, rather versus in the case where only 5 pixels were being perturbed. It was much lower on average in terms of success rates. So definitely grew with number of pixels.
So when the images are much larger compared to how much you perturb, the trick is trying to figure out how minimal you can be in doing it and still be successful.
Yeah, that would be like the ideal goal of changing few enough pixels by a small enough amount that it's still imperceptible while still modifying the model's prediction.
So other people could continue on this pretty easily if they were interested.
Yeah, absolutely. Everything's available online now.
There's a question from Troy in the chat. He says, have you looked into any adversarial attacks in self-driving car data or images during your research?
No, but it's something that I've read and heard a little bit about. Like, it's not something I've looked a lot into, but it's like the idea of like, covering up a few spots on a stop sign and like the car being fooled, right? I mean, it seems really dangerous to me, although it's not something I have like learned a lot about.
Any other questions? Yeah, scary, says Troy. Definitely. I wonder if blizzards look for Shapley values and how much they block out. Okay, thanks a lot, Cameron. That was really interesting.
Thank you so much. I unfortunately have to leave for class, so I won't be able to watch the rest of the presentations. Thanks, everyone.
Okay. And earlier I didn't mention Lance Galetti, but Lance Galetti was the mentor and the instructor who helped these students. And so people who are interested in continuing should certainly reach out to him or to us, and we'll get you in touch with him as well.
Yep, that's me, for those of you who haven't met me yet.
Yeah. And I'm sorry, my video is frozen here, so I can't see you waving, but hopefully you were waving, Lance.
I was.
Good. Okay. So Christina Zhu is our next presenter, and she is going to be presenting on differential privacy. Christina?
Thank you. Can you see my screen?
Yep, it looks good.
Okay. So machine learning models have a tendency to memorize sensitive data. It was shown that in order to achieve high accuracy, these models sometimes memorize seemingly irrelevant information, ultimately compromising users' privacy. And this sensitive data, including personally identifiable information, can later be exploited by an adversary. So a model accidentally memorizing social security numbers, for example, can provide a glaring opportunity for identity theft. However, access to data and data analysis help drive important decisions that improve society. So it's unrealistic to completely get rid of data analysis, which is why we're faced with the challenge of releasing information that benefits society while making sure that individual information stays hidden. Hi, my name is Christina. I'm a third-year statistics student at BU, and today we're going to be looking at differential privacy, a technique that can be used to protect users' privacy in machine learning. We're going to look at why traditional privacy-preserving methods don't work, an intuitive and formal definition for differential privacy, how companies fail to properly implement it, and how we can educate users on differential privacy so that they regain control over their own privacy. So one of these traditional methods to preserve user privacy is to only release aggregate information. Any statistical query on a data set will leak a small amount of sensitive information about each individual because we want to learn something about them. However, too many overly accurate statistics can completely violate privacy in a phenomenon known as the fundamental law of information recovery. The US Census Bureau is faced with this challenge every 10 years because they need to release billions of statistics on a population. Left unattended, an adversary can launch a reconstruction attack to recover part of the entire data set based on the statistical summaries revealing individual records. In order to exemplify that, let's look at a toy example. So suppose we conduct a census survey on a neighborhood of 4 people, and we collect basic demographic information on them, such as their age and race, and we publish aggregate information. The goal of an adversary in this context would be to reconstruct our original data set based on the aggregate information that were released. And based on the count column, an adversary would know that 2 people in our data set are age 30, and they would consider 3 different cases in order to figure out their races. The first one being that they both identify as Asian, or 2, they both identify as Black, or 3, one of them identifies as Asian and the other identifies as Black. Based on the mean age column, the adversary would come to the conclusion that only the third case, where one of them identifies as Asian and the other identifies as Black, is possible. So as you can see, simply releasing aggregate statistics is not sufficient enough to protect privacy. A second attempt at preserving users' privacy is anonymizing the dataset or removing obvious identifiers. In the previous examples, we purposely failed to collect the individual's names in an attempt to anonymize the dataset. However, similar to releasing aggregate statistics, removing obvious identifiers is also not enough to preserve privacy. There will always be sufficient auxiliary information that can be used to identify individuals in a dataset, and an adversary can re-identify them by purchasing or stealing commercial data and linking the reconstructed dataset with the commercial dataset based on the same records, successfully re-identifying the individuals. Here's a visualization of that process. So how do we provide rigid privacy guarantees for users? Well, first let's define what privacy means in the context of differential privacy. On one hand, complete privacy is equivalent to no data analysis being performed at all. And in order to guarantee this, we would have to ensure that the model never looks at data, defeating the purpose of ML models, which is to make predictions based on data. So we want to shift our goal from achieving complete privacy to publishing useful data analysis while guaranteeing a limit on individual privacy loss. In other words, we want to learn something useful about the population from the data without learning about a specific individual within the population, which serves as our intuition for differential privacy. In order to make a mechanism differentially private, we have to add some sort of randomness or noise to part of the process. Suppose we were then to remove an individual's information from our dataset, in this example, Bob's, and run our new mechanism on it. If the probabilities of output are similar, then we can say that our new mechanism is differentially private. So how exactly does this protect privacy? Well, an adversary looking at the probabilities of output would have a difficult time locating Bob's presence in the data set because the probability of outputs are so similar. So as a result, we were able to hide Bob's presence in the original data set, thus protecting his privacy. More specifically, we say that our model is epsilon differentially private if the probability of outcomes on a pair of neighboring data sets D and D prime only differs by a factor of exponential epsilon. Epsilon is our privacy loss parameter, and the larger the value of epsilon, the less privacy protection is provided by the algorithm in favor of more utility. Conversely, the smaller the value of epsilon, the more privacy protection is provided at the expense of utility. So why the hype? Why is differential privacy the leading technique to address users' concerns for their privacy? Well, differential privacy allows for composition, meaning that you can quantify the total privacy costs over multiple analyses by adding up the privacy costs of each individual analysis. And this allows us to build more complex DP algorithms using simpler ones. Another cool property of DP is that it's closed under post-processing, meaning that an adversary can't worsen or reverse the privacy protection provided by a DP algorithm by performing any arbitrary function on the output. As a result, we can safely share and also discard of data. Despite all these conceptual advantages, companies still fail to properly implement DP. In the case of Apple, they use local differential privacy, where the user's device inputs random noise in the user's information before that information gets uploaded to Apple servers. However, Apple suffers from a lack of transparency. The effectiveness of DP depends on the value of epsilon, which Apple has kept secret. As a result, users can't make an informed decision on whether to opt in on data collection. And Apple can change the value of epsilon without users' knowledge or consent, potentially worsening privacy protection in favor for more analysis. It took a significant effort from researchers to reverse engineer Apple systems and uncover Mac OS's daily privacy loss of 6 and iOS's daily privacy loss of 14. These choices of epsilon are extremely concerning because academics typically view any value of epsilon over 1 as a serious privacy violation. And based on the composition property of DP, a user's privacy risk increases as uploads are made every day. So suppose an individual with a rare medical condition inputs this information on his phone's health app. Their phone would upload this information to the server on a daily basis using differential privacy with an epsilon of 14. After one upload of noisy data, the company would be able to identify this individual with 50% certainty. And after just 2 days, they would be able to do so with 100% certainty. And over the lifetime of the individual's device history, they would experience infinite privacy loss. So as you can see, when your choice of epsilon isn't meaningful, you're only achieving differential privacy in name and not in actuality. So how do we incentivize these companies to properly implement differential privacy? Well, we know that companies are more likely to respond to consumer demand compared to pressure from researchers and academics. So what if we could educate users so that they could examine the current deployments of DP more critically? One of the major barriers preventing them from doing so is that current definition descriptions of DP set inconsistent and oftentimes inaccurate user expectations due to their varied language. This motivates a need for new descriptions. And that is what I'll be working on this semester with other professors at BU who specialize in DP. We hope to develop better descriptions that directly and accurately address users' privacy concerns. And it was shown that users are more likely to understand differential privacy when provided implication descriptions instead of definition descriptions. And we also hope to document the history of grievances that the public has had with DP data analysis in order to address them. Thank you all for listening. Thank you to Lance Galetti for his mentorship, and thank you to all my peer researchers for providing a supportive learning environment. And thank you to Red Hat for funding this project and making my research possible. If you're a math nerd and you're interested in the underlying math behind DP, I published a blog series on Medium about it, so definitely check that out. Thank you all for listening. Are there any questions?
There's a question from Ari in the chat. He says, well, actually, you're here, Ari. You can say it. I don't need to read it.
I didn't know whether to just chime in. Thank you. It was a very nice presentation. You did a very nice job. Do you know how researchers were able to reverse engineer the epsilon values for macOS and iOS?
I'm not too sure of the specifics, but they definitely had to have like access to Apple's code. I linked the research paper where I found this information from in my presentation if you're interested in reading it. But one thing I do remember reading is that it took like 14 researchers and 6 months to accomplish that.
Yeah.
So like significant effort, and it kind of undermines one of the conceptual advantages of DP, where users can just see the value of epsilon and like make an informed decision. So given that Apple doesn't like provide that information to users, Apple's implementation of DP is meaningless.
Yeah. Also, the code is not open; it's proprietary, so it'd be very difficult to get that information. But it's very interesting. Thank you.
Other questions? I'm happy to hear that you're continuing with this, Christina. That's great. I hope you come back and update us again. That was a great presentation.
Thank you.
And our final presentation today is from Anki Lin, who will continue to explore the question of adversarial attacks as a solution to privacy.
Thank you so much. Let me share my screen. Can everyone see it?
Yes.
Okay. All right. Hi, everyone. My name is Anki Lin, and then I will be presenting the work that I've done last semester to answer the question of, are adversarial attacks a viable solution to individual data privacy? So first, I would like to introduce the goal of this research, which is to develop tools that help users regain control of the data they submitted to the platform. As a user that doesn't trust platforms to implement privacy-preserving solutions on their end, what the tools are available today to remove sensitive information from the data they submit to the platform. And the reason why data privacy matters is because one example of that is because of the exponential growth of technology. So the data users submitted today is subject to the scrutiny of future cutting-edge tools. Given an example, 20 years ago, if I gave data to a company, they can now use facial recognition to identify every single person in the picture in a way that I didn't consent to 20 years ago. The idea is that we want to find ways to build a tool to remove sensitive information from the data before you uploaded them to the platform. One of the fields we explore is adversarial learning. During the talks, I'll discuss different adversarial techniques today and investigate alternative approaches to generate adversarial texts that are more relevant to this context. Specifically, I'll focus on what's black box models, white box attacks, Shapley values, and how I've done experiments to further understand the traits of the adversariality of black box models. So adversarial attacks can be divided into two kinds, which are white box attacks and black box attacks. A white box attack is a scenario where the attacker has complete access to the target model, including the model's architecture and its parameter. On the other hand, a black box attack is a scenario where attacker has no access to the model and can only observe the outputs of the targeted model. I created this visualization in order to capture the recent popular black box attacks. So typically, black box attacks have three categories, as you can show on a graph. The first, transfer-based methods, does not rely on model information, but it needs information about the training data. For score-based method, the only knowledge about the attack model are the input images and the relative output confidence scores, which the confidence scores is the accuracy of the model correctness. The third method, decision-based method. Under this setting, the only knowledge the attacker has about the model are only discrete hand-labeled predictions. In short words, the goal of this method is to obtain an adversarial image that, for instance, looks like a cat, but let it be misclassified as a fish. As mentioned in the previous slides, most of the tools that are not practical for today to use, because it requires information about the training data or the confidence score to implement the models. To answer the question of where's the information come from in the image, what's the best guess? Can we make educated modifications to images without knowing the confidence scores and the training data set? I need to first introduce the concept of Shapley value. The Shapley value is a solution concept in cooperative game theory. It was named in the honor of Lloyd Shapley, which is the person on the right-hand side on the slide. He introduced it in 1951 and won a Nobel Prize in economics for it in 2012. But as Cameron mentioned earlier before, we use this to understand why Shapley value attacks makes the prediction they do. So Shapley values, why black box attacks make the prediction they do. Shapley values as a metric to understand if pixels of the image that contributed positively or negatively towards the model's decision, which help us to seek for common traits of the adversariality of black box models. So in my research, I try to investigate how changes of the neural network architecture affect the neural networks learn by looking at the changes of the Shapley values. Two of the experiments I ran last semester was to change the number of neurons and try different activation functions by keeping everything else constant. The first experiment I've done was to triple the number of neurons in the model, as you can see on the slide. My prediction was that the number of neurons is triple, then the pink Shapley values will be between the gap of the pants, which the pink values means they are positive Shapley values. They contributed positively towards the model's decision. My hypothesis was like that because the gap in between the pants is like the most obvious feature of the pants when the model tried to identify what that image is. However, I found something interesting is besides there's more pink values in the middle, there's a cluster of pink values on the right side of the visualization. From my understanding, I suspect that's because I only have triple the number of neurons. the visualization wouldn't show obvious change between the Shapley values with the original image. So I 10 times the number of neurons later on. Here is the same experiment, but with different pants graphs. And I haven't mentioned about the blue values. So the blue values are negatively Shapley values. It indicates the pixels contributed negatively towards the model's decision. So when I triple the number of neurons, the pink value seems to be less. My explanation of that is because the model figured that the left-hand side of the pins wouldn't contributed negatively towards the model's decision. As you can see on the graph on the right-hand side, there's less blue values. It's neutral, so the colors are less saturated. The next experiment I've done was to 10 times the number of neurons in the model. My prediction was that when the number of neurons is 10 times, the pink Shapley values will only be distributed between the gap of the pens, as I mentioned earlier, because the gap in between the pens is the most obvious feature of the pens. However, something that's not unexpected is pink values are mostly on the edges of the pens when I 10 times the number of neurons. This actually makes sense to me because in order for the model to identify what's a pen, it has to figure out what the edges of the pens look like. So, given an example, when we first learn how to draw a pen, we start from the edges, right, and then filling out the circles, the colors, and other details in between the pens. By looking at the blue values, so as expected, like before, the blue values are less when I 10 times the number of neurons. The distribution is also even and neutral, and the colors are less saturated. So it means there are less pixels contributed negatively towards the model's decision. The third experiment I've done was to keep everything else constant in the model and only change the different types of activation functions, which there are sigmoid, 10H, and the ReLU activation functions. My expectations are sigmoid's activation function model and ReLU's activation function models visualization will look alike because their values are always positive. But 10H's value is between -1 and 1. Yet the results turn out that the sigmoid and ReLU activation functions visualization of Shapley values don't look alike. For sigmoid activation function on the left-hand side, as you can see, there are more pink values and it's evenly distributed. And for the ReLU activation function on the right-hand side, the pink values are in between the legs more. And for the 10H activation function visualization, it's like the pink values are also more distributed in between the legs. Based on my current understanding, I think it's because I think it's best to use the 10H activation functions because other than having pink values in between the legs, there are also pink values on the edges of the pens, similar to what happened when I 10 times the number of neurons. And this is the same experiment. Let's look at the blue values now, the negatively Shapley values. For sigmoid activation function, there are more blue values and it's mostly in between the legs. For ReLU and 10H, the blue values are less saturated and evenly distributed. Based on my understanding, I think why sigmoid Shapley values look like that is because the sigmoid activation function has the problem of managing gradient. So during a neural network's back propagation, on moving towards deep learning networks, the gradient becomes very close to zero. And if it reaches zero, no learning happens, which I think that explains why sigmoid's visualization looks like that. However, it's still an open research area, and we are still trying to figure out how to understand the Shapley values and its relationship between black box models in a meaningful way. So here's how you can get involved and my next step. So we have a repo with experiments we've done previously, as Cameron mentioned before, and we have a KVIS visualization GitHub repo as well, and we have a Slack channel with all of our research team members. So if you're interested in, please get involved. Thank you so much. Yeah.
Any questions for Anki?
There's a question in chat, Heidi, or a comment.
Yes,
Yeah, I
from
see.
Alistair. It's not just the pixels in the pants, though. It's the alternative images in the data set that it's not matching against. Question mark. Sorry.
Oh, I see. Yeah. Could you clarify the question more? That is.
Yeah,
the
Alistair,
last
can you
one.
join? Can you turn on your
The
audio?
microphone on? Yes. Okay.
Thanks.
Yeah. Yeah. So where you've got some of the blue dots down the outside, and you haven't on the other side, maybe some of the other images in the data set, like there might be a bag that goes across more to the right than the left. So the pixels on the right tell you it's not a bag, whereas the pixels on the left don't tell you it's not a bag because they're not in the bag. You follow?
Oh, yeah, yeah. I think that's also a reasonable explanation. Thank you for pointing that out. That's something that didn't trigger that, like, observed before. But thank you so much.
Anki, can you tell us what made you interested in investigating privacy in the first place?
Well, I think I was affected a lot by our research team. So it was like, so Lance pointed that out, that topic, and we all found that's pretty interesting. And Cameron started doing his experiment earlier than me. So I stepped in and collaborated with Cameron to do a deeper investigation on Shapley values and its relationship with black box models. And I think it's an important topic nowadays that most of the users overlooked the question of data privacy. So yeah, that's my motivation.
Yeah, definitely. It's unusual to have a presentation where all of the ML topics are about privacy. This is great. We've had some people who worked on differential privacy and multi-party computing, both techniques for preserving privacy as part of Red Hat Research Days before. And there are ongoing projects there too at BU. So I'd love to have students and people involved in those projects going forward. So it's really, really great to see undergraduates doing this kind of stuff. Thank you, Anki. Any other questions?
Yeah, if I can just chime in, I mean, we sort of monopolized the meeting today. Yeah, I guess just to provide some perspective, I mean, first I want to say, like, I've been super lucky to work with these really bright students on some work that I think is really meaningful. As a whole, like, our research group is focused on increasing the prominence of privacy conscious tools. And we've sort of approached this from like two perspectives. The first perspective is from the company side, you know, what tools can you use to protect the privacy of individuals that trust you with their data? And then from the user side, you know, what can you do as a user that doesn't trust platforms to protect your privacy, but still use the platforms that exist today? And yeah, so that's sort of the context, right, of like this whole research project. And I can't emphasize enough, like, how amazing Cam and Anki and Christina and Maria are. They started, you know, from like not knowing. I mean, the learning curve was very steep, and what they've overcome to present what they did today is really incredible. And I hope that, you know, if you're a student on this call and you don't think that you can get involved in this sort of research, you know, think again. Definitely reach out, and I'll be happy to point you to some resources. We have a great Slack channel which is very supportive, and we all went through it. We all had to learn all this stuff. So we have a good number of resources now, and hopefully the onboarding isn't too difficult. But yeah, anyway, please reach out.
Thanks, Lance, and thank you for bringing us together. We'll be posting this video on YouTube so other people can look at it. Other students, feel free to share that. It'll be going up on research.redhat.com as well, the link to the presentations as well as the video as soon as we get that posted. So really appreciate you guys attending today and sharing really good explanations of differential privacy and random noise too. That was fantastic. And I hope we see you again on other projects in the future. Thanks a lot.
Thank you.